All right, so what about this? What about a problem like this where here's a real practical problem that you might do. So we've got an electric circuit. P is the output power. And B is voltage. Okay, so that's a potential difference, voltage. And then R1 and R2 are just the resistances of two resistors in this circuit. And these are just resistors that are in series. So all this circuit is, if you want to look at it in terms of like a circuit diagram, you're just going right, there's one resistor. I'll just write it this way for you guys. And there's the minus and there's the plus. So that's really all it is, right? So what are the variables then? So everything's constant except R2. So that's a variable. And then, of course, that's the output variable, right? So what am I going to do? We can do this. This is pretty cool. We can do this. Even now, we can do this problem. This looks a lot like, I mean, we might normally, this might be replaced with something like f of x, and those are x's, and the other stuff are just numbers, right? Just constants.
Take a derivative.
Take a derivative. Yeah, let's take a derivative. So p prime is going to equal what? What about the VR1? What about that?
It's just a constant.
It's a constant, isn't it? Right. We don't know what the value is, but it's a constant. So what do we do with constants when we differentiate? Pull them out front and leave them there, right? So the only thing we've really got to deal with is just this quotient, right? Okay, so let's do that first of all. Let's just pull those out front. What we've got left then, and we wouldn't have to. We could just leave them as a part of the top, but that's what we're differentiating it is that quotient, right, in yellow. So what's that going to look like? I'll put the V R sub 1 there, and then whatever we get from the quotient rule, we'll just put in the script brackets. So what is the quotient rule here? Low D high. So low is just all this stuff. So I've got the quantity R1 plus R2 squared times the derivative of the top, which is
2.
okay. So this is going to be just an R2. So if I'm differentiating with respect to, what am I differentiating with respect to here? Let's write this derivative out a little differently. So let's write this, instead of just writing prime, I think this time it's worth our writing it as a fraction, right, in the ratio form. So we're taking dp, d what?
First of 2.
dr, yeah, right? We're going to tweak the value of r. Okay? And okay, so then what are we going to get? Okay. What's the derivative of R2 going to be with respect to R2? 1. Right? So that one we don't have to worry about. That one goes away. Minus top, right? Which is R sub 2 times the derivative of the bottom. Well, what's that? 2 times, if we have hand squared, right, the derivative of hand squared is 2 times hand, so we get 2 times R sub 1 plus R sub 2 times the derivative of what's inside, which is just 1, right? Everybody good with that?
No.
So what's the derivative of R1 plus R2 with respect to R2? Now imagine that's an x. we're differentiating with respect to x. If we had the derivative of a constant plus x with respect to x, well, the derivative of the constant is what? 0. What's the derivative of x with respect to x? What's the derivative of R2 with respect to R2? 1. Okay? And really there's a 1 there too, I guess, isn't there, if we want to write it. All divided by what's on the bottom.
R1 plus R2 40.
Squared is to the 4th. Okay? Right, so there's our first derivative. Well, let's clean that up. Okay, if we clean all that stuff up, what do we get? So we get VR1 times, I would have to, well actually look, I could factor out an R1 plus R2 on the top. If I clean this all up, what I've got doesn't change it much. I've just got R1 plus R2 squared minus 1 times 2 times R2 is just 2R2 times R1 plus R2 over R1 plus R2 to the 4th. Okay, so what do we do in situations like this? This goes back to, last chapter, right? How do we simplify something like this? What are we going to do, Glenn? Okay, we're going to factor out the greatest common factor from the top. Well, look, we have like bases, don't we? We have an R1 plus R2 to the 2 and to the 1. So I can factor that out, right? And then we end up with VR1 times R1 plus R2 to the 1. We can go ahead and pull out this common denominator too, can't we? Right? If we want. Well, we'll just put all of this over the common denominator. R1 plus R2 to the 4th. Well, what's left over if we factor those out? From the first term up here, let's put a circle around that minus so we keep track of it. What's going to be if I undistribute or factor out an R1 plus R2 to the 1, what's left from the first term?
R1 plus R2.
Good. R1 plus R2, right, to the 1. What's left from over here? Second term, there's our minus.
2R2.
Yeah, 2R2. Okay, well, look what we can do now. Algebraically, there's some cancellation, right? So we could cancel this top and bottom. What does that power become? 3. Because I'm canceling like factors. How many factors are there on the top? 1, 2, 3. Right? This one we can clean up, but it's just a factor, right? It's this, everything in yellow is being multiplied by this, which is being multiplied by the constant, right? Okay, so then, where does that leave us? On the top, we've got VR sub 1 times, what is all this going to become? I've got R1 plus R2 minus 2R2.
R1 minus R2.
Yeah. All divided by the bottom cubed. Okay, so what about our domain? You guys really don't know much about circuits at this point, but what can you tell me about the resistance of a circuit, of a resistor? Resistor is just any circuit element. Like if this could be for a light bulb. I mean, a light bulb, if you put a light bulb in the middle of a circuit, and all the circuit is, say it's driven by a battery. That's what we call in physics an electromotive force. It's just going to drive a current around the circuit. If you put a light bulb in there, what does that do to the circuit? Well, it's a resist. It has some impedance. It's going to resist the flow of electricity through there because you have to push to get the electrons through there. But as they go through there, what do? They light up the light bulb, right? And there's some power output from that. Like it might be a 60-watt bulb or a 100-watt bulb. Watts are a measure of power, right? And this is just a quick tutorial. I mean, you guys aren't going to be, engineers at the end of this lesson, but you get the idea then, right? That anytime you put a circuit element in there, it's going to act as a resistor, right? So what's the resistance if you put in the tiniest, like this little tiny LED light bulb? It's gonna take very little power to drive that, and so the resistance would be very small, right? But if you put in a burner from a stove, well, it's really hard to drive the electrons through there. There's a lot of resistance, which is why it heats up. Okay, so that's gonna have a huge resistance. So what's the smallest possible resistance, do you think? I mean, it would approach zero, right? If there were nothing there, it would be a resistance of zero. But you couldn't have negative resistance, right? You're not gonna somehow just generate more electrons out of nowhere. So the resistance, if you look at the variable R2, the domain is just gonna be R2 is what? You know, greater than, or maybe you could argue greater than or equal to zero, but that's it, right? So now let's go down and look at our derivative function. Or look at our function, I guess. Are there any parts of this domain that would have to be eliminated then? Well, no, right? If R1 is some non-zero resistance, let's just say we're assuming that R1 is greater than zero, and R2, if it's an actual resistor, let's just say it's greater than zero, it makes it easier to think about, then there's no problem, is there? There's no way we can get zero on the bottom. So this domain is fine. The function's going to behave fine over that domain. What about our derivative? Let's look for our critical numbers. If this is dp, dv, oh no, sorry, dr2, wasn't it? I don't know if those are ours, yeah. Okay, let's just look at this and find the critical numbers. Okay, on our domain, is there any place where our derivative is going to be undefined? Any place where we're going to have zero on the bottom? And remember that both R1 and R2 are greater than zero, right? The resistance is greater than 0 ohms. So, yeah, there's no place where our derivative is undefined, right? So P prime is nowhere, this is how we say it in math, is nowhere undefined on our domain. Okay, where does it equal 0 though? P prime equals 0 when what happens? R2 is the only variable here.
And R2 equals R1.
Yeah, everybody see that the only way, you know, V1 times R1, those are just constants, right? Those are non-zero constants. The only way that this can equal 0 is when the top equals 0, which happens when the yellow factor is equal to 0, right? The only way that P prime can equal 0 is when R1 minus R2 equals 0, which is when R2 equals R1. That's our only critical number, isn't it? Right? So then let's make a table. Let's make our table and see if we can establish what the behavior of this function is. So now, and I like that we're doing this. This is, I know, trust me, I know that you're looking at this right now saying, wow, this is kind of probably even hard to follow a little bit. But I want to show this to you, and let me explain myself. I think that helps. I want to show this to you because this is a glimpse of your future. This is where we're going in section 3.6, I think it is in our book. When we do optimization, this is an optimization problem, right? This is where we're going to try to use our tables to find relative extrema for actual real-world mathematical models. Like in this case, it's a resistance model, right? So what does our table look like here? Instead of an x, what's our independent variable? R2, wasn't it? Right, R2. So our first row is just going to be R2. Our second row is what? What's our output? Instead of y, what's our output? P. And then third row is, whoops, not R, is P prime. Okay, so what's our domain for R2? Well, we just said it's everything greater than 0, right? there was only one critical number on our domain, and that was R2 equals R1. That was a 0 for the first derivative, right? Which means we have a horizontal tangent line. We just need to know what kind of, critical number is that, right? So we need to pick some test points. So let's just pick some test points. What if we pick, what would like a test point look like here? We don't know what R1 is. But what's a number that's bigger than R1?
R1 plus 1.
R1 plus 1, or what's another one?
R1 plus 2.
Okay. What's one we could create by not adding something to R1?
R1 squared.
R1 squared, or 2 times R1, or something like that, right? So we just want to pick a value that we know is bigger than R1, and let's pick one that's going to be easy to plug into our function, right? We want to evaluate our derivative at these test points. It would probably be easiest to pick one, we're picking a value for R2, right? Wouldn't it be easy to maybe pick a value like 10 times R1? Does that make sense? Because then if I had R1 minus 10 R1, I just get minus 9. See what I'm saying? That would be a compatible one with our derivative function. So let's pick a test point like 10 R1. And what about down here? Well, I can't pick negative because I bottom out at 0. But what would be between 0 and 1 R1?
1/10 R1.
1/10 R1. Sure, we'll do that. Okay? Well, let's just look at the signs of our first derivative. That's all we care about are the signs, right? So if we go up here and let's just carve out a little space on the board. So P prime of R2 equals that, equals V R1 times R1 minus R2 over R1 plus R2 cubed. Okay, so what is P prime of 10 R1 going to look like in terms of signs? What's going to be the sign of the top? We know that's positive, right?
It's gonna be negative on top.
So it's going to be negative, isn't it? I'm going to get something like R1 minus 10 R1 is negative 9 R1, but R1's positive, right? Everybody see that makes the top negative? What's the bottom always? Positive. Negative over positive is negative. Okay, so for our first, the sign of the first derivative here is negative. Don't care about the value. It's negative. What about at our other test point? So now we've got P prime of 1/10 R1. Well, if I plug that in, what am I going to get? I'm going to get a positive times R1 minus 1/10 R1. What's R1 minus 1/10 R1?
9.
9/10 R1, and R1's positive. So what's the sign of the top? Positive. Positive over positive is positive. So using the first derivative test, what is that critical number? If I'm going from, what does this mean if on this entire interval here, the first derivative is positive? It means it's increasing, right? Over here it's what? For the rest of the function, all the way out to infinity, it's decreasing, and so increasing to decreasing looks like what? A smooth maximum, yeah, right? Isn't that cool? So we just figured it out. That's got to be a maximum. That's our only maximum for power. And it happens when, at our critical number, which is when R2 equals R1. So when the resistances match, that's going to maximize the power output of that circuit. That's pretty cool, I think, isn't it? I mean, that we can do, that's real math. And this is like, this just isn't all, everything you've done up until now is pretty made up. But this is like real math, right? Okay, I like that.
How would you answer the actual question?
So the answer, well, okay, what was the actual question? Let's go back.
It's like,
So the actual question is, Yeah, they wanna know if V1 and R1 are held constant, what resistance R2 produces maximum power? R2 equals R1. Whatever R1 is, that's what R2 should be, if you wanna maximize power output.
I
Okay,
know that just because it's the maximum of the graph.
yeah.
Okay.
And so if you're, like when you're building your first, DIY tube amp at home and you want to maximize power output in a certain channel, well, now you're gonna know what kind of resistor to buy from the online electronics shop, if you're, so,
I don't know.
maybe that needs to be our high school post-grad class is gonna be building rear-driven horn speakers and, I don't know, and DIY
Running.
tube amps and,